In this video, we're going to talk about how to deal with complex numbers. So I'm going to actually solve this first example as if I weren't using a calculator, but I want to mention that my default strategy is in fact to go to the calculator first. So unless I have a reason not to, the first thing I would do in this case, if I needed to factor this or to find all its zeros, would be to stick it into a calculator or to some sort of graphing tool. You can find ones online as well. So I'm going to type this into my calculator. 13x cubed negative 23x squared minus 14x minus 24. And have a look at the graph. You may need to, depending on the polynomial, widen your search, your x minimum and x maximum to see all the zeros. But I can see 3 here. So looking at this, none of these bounce. These all cross the axis, which means these all look like they have multiplicity 1. I can't see the whole graph, but I don't need to, because all I need to look at is the zeros. Looks like 1 at -3, 1 at -2, and 1 at +4. So even if I were going to do the synthetic division by hand, which I will be doing, I don't need to try every single potential zero. I can focus on the ones that seem most likely to reduce the complexity of the problem before I get to the hard ones. -3, -2, and 4. Now actually approaching this one by hand, I might start with the rational zeros theorem. So all my zeros are going to be factors of 24, plus or minus 24. So -3, -2, and 4, all of which I identified from the graph, are all candidates according to the rational zeros theorem. I'm not going to, normally I start with 1 and work my way up if I have to do it by hand. But because I already know 1 and 2 and 3 aren't going to work, I'm going to start with 4, which looks on my calculator like it'll work. 1, 1, -13, -23, -14, -24. I suppose I should preface this by saying I identified on my calculator only 3 real zeros. And this is a 5th degree polynomial, which means there's 2 missing. Theoretically, it's possible that there could be one that's bigger than 10 or one that's less than -10. Although in this case, I'm fairly certain they are complex. They're imaginary, which is why there are no x-intercepts. In order to find them, I have to break this polynomial down to where what I have left is the irreducible quadratic. So I'm going to proceed. That's 1, 4, 5, 20, 7, 28, 5, 26. Uh-oh. Did I mess up? 1 times 4, that's 5, 27, 2 times 4 is 28, 5, -14, plus 26. Oh, I'm an idiot. That's 24, which makes 0. And I don't know why I thought that wasn't going to work. So now I have partially factored my polynomial, x minus 4 being the first factor there. The next factor being x to the 4th plus 5x cubed plus 7x squared plus 5x plus 6. So as I proceed, I'm going to use the quotient from my previous synthetic division, not the original polynomial. I'm breaking it down. I already know I'm already expecting -3 to work, so I'll try it next. 1, -3, 2, 6, that -6, 1, -3, 2, -6, 0. Excellent. And is the other one -1, -2? Yeah, -2. So I'll do that finally. 1, 2, 1, 2. So that's 1, -2, 0, 0, 1, -2, 0. So I've got x minus 4, x plus 3, and x plus 2. If I were doing this by hand, I would have a whole lot more synthetic divisions, most of which failed. But I have now reduced this to x minus 4, x plus 3, x plus 2, and the remaining factor is x squared and 0x and 1, which has no real zeros. Since it's quadratic, I can find the remaining zeros using the quadratic formula, although since there's no b, you could also solve this one by subtracting the 1 to the other side and taking the square root of both sides. So the square root plus or minus square root of negative 1. The square root of negative 1 is I, so this is plus or minus I, which means my zeros are positive 4, negative 3, negative 2, I, and negative I. 1, 2, 3, 4, 5. 5 zeros, 5 complex zeros. This right here, we call this factored to linear factors and irreducible quadratics, because you cannot reduce this quadratic. You cannot factor this quadratic over the real numbers. So it's called an irreducible quadratic. So this is all linear factors and irreducible quadratics. If you need a complete linear factorization, you have to use imaginary numbers as well. So x minus 4, x plus 3, x plus 2. This one factors as x plus I and x minus I. And this is a complete linear factorization. Notice it uses imaginary numbers because we need those in order to factor this part of the formula. So basically as a general rule, if there are complex numbers, as long as there's not more than 2, you can use synthetic division to get all the rational ones, and then either the quadratic formula or some other method to solve the last 2 for either finding all the zeros or all the linear factors. If what you're doing is just factor it to linear and irreducible quadratics, you can stop here. You don't actually need to use the complex numbers. Coming at this again, I have an example that has only imaginary zeros. If I graph this one, x to the 4th minus 6x cubed plus 35x squared minus 50x minus 58, you're not going to see... Oh, wait. It does have 2. I was wrong. Oh, I see. They're not rational, I believe. So it has 2 real zeros. It has 2 complex zeros. But this is a slightly different problem because at the high school level, we're not going to expect you to necessarily break this polynomial down unless you've been given one of the zeros. So 2 plus 5i is a 0. Now the conjugate root theorem says that if I have rational coefficients and one of my zeros includes a square root, then its conjugate also is a 0. So the fact that 2 plus 5i is a 0 tells me that 2 minus 5i is also a 0. So by giving me the 1, 0, they've actually given me a pair. That doesn't work for rational zeros, but it works for irrational or imaginary ones. So I can do synthetic division using an imaginary number. And you may not like it, but you're going to have to do it if you are in my class. So might as well get started. 1x to the 4th, negative 6x cubed, 35x squared, negative 50x, and negative 58. I might have wanted to leave more room. We'll see how it goes. So I bring down the 1. Now when I multiply, I do 1 times 2 plus 5i, and I get 2 plus 5i. I definitely wanted more room. Then when I only combine like terms. So this is negative 4, and the 5i just hangs out. But when I multiply negative 4 plus 5i times 2 plus 5i, I'm going to have to FOIL. So let me do that over here. 2 plus 5i times negative 4 plus 5i is negative 8, and 10i minus 20i plus 25i squared. Hopefully you remember I squared is negative 1. So this is actually negative 25 and goes with a negative 8 to make negative 33. and 10i minus 20i is negative 10i. So this is negative 33 minus 10i. So when I add 35 and negative 33 is 2, and I've got minus 10i. So now I have to do 2 plus 5i times 2 minus 10i. That's going to give me a 4 on the, well, I'll write it out. 2 plus 5i times 2 minus 10i is 4 minus 20i plus 10i minus 50i squared. That's going to be plus 50 because I squared is negative 1, which gives me 54 and 10i. So this becomes positive 4 plus 10i. So then I'm doing 2 plus 5i times 4 plus 10i, which is 8 and 20i. Uh-oh. Oh, that was supposed to be minus 10i. Yes. That's minus 10i, and so is this. So is this, which makes this minus 20i plus 20i minus 50i squared, which becomes plus 50. So 58, and no i's left over, which is important because I'm supposed to get 0 at the end if this is actually a 0 of my polynomial, which it is. Everything worked out. Although I do have complex coefficients here, which there's no way around it until I also synthetically divide by the conjugate. Which, when I put this in, I've got negative 4 plus 5i now. I'm going to space it out a little bit more. This is 2 minus 10i, and this is 4 minus 10i. When I do synthetic division again with the conjugate, all of the i's should go away. So I bring down the 1. This is 2 minus 5i. Negative 4 and 2 makes negative 2. 5i and negative 5i cancels. So now I've got negative 4 plus 10i, which again, that's negative 2 and nothing. And this is negative 4 plus 10i, which is 0, as expected, leaving me with x squared minus 2x minus 2. So I've got x minus 2 plus 5i and x minus 2 minus 5i. And x squared minus 2x minus 2. Multiply to negative 2 and add to negative 2 is unlikely for rational numbers. So I'm going to use the quadratic formula to find my last two zeros. Opposite of b, plus or minus the square root of b squared minus 4 times a times c. That's plus 8. So 4 plus 8 is 12. Confirm that's not rational, but that is 4 times 3, so the square root of 4 is 2. So 1 plus or minus the square root of 3. So again, depending on your instructions, in this case, find all complex zeros. I just have to make a list. 2 plus 5i or minus 5i, and 1 plus or minus the square root of 3. That's all 4 complex zeros. 2 of which are imaginary and 2 of which are irrational. I wouldn't expect you in high school to be able to find any of them. You could approximate them using the calculator, but I wouldn't expect you to be able to find any of these without getting at least one to get you started, because all 4 of them are irrational. I should say all 4 are not rational. 2 of them are irrational numbers, and 2 of them are complex. Well, imaginary. Okay, we're going to do the same thing now, but in reverse. We're going to write a polynomial function of least degree, the smallest we can, with real coefficients in standard form that has these as zeros. That's negative 1, 2, and that is 2 minus I. It's a little bit messy there. So the first two are easy, x plus 1 is a factor of my polynomial, and x minus 2 is a factor of my polynomial because they're zeros. 2 minus I is a 0, which means x minus 2 minus I is also a factor of my polynomial. But as we said before, these always come in pairs, conjugate pairs. So what I know because of the conjugate root theorem is that x minus 2 plus I is also a factor of my polynomial. If 2 minus I is a 0, 2 plus I is also a 0. At this point, I have to multiply all this together. I'm going to start with the conjugate pair, because when I multiply those together, what I get is going to be real, guaranteed every time. So this is x minus 2 plus I, and this is x minus 2 minus I. When I multiply negative I times positive I get negative I squared, which is positive 1. Oh, which means I should put it over, well, it's fine. Negative I times negative 2 is positive 2i. Negative I times x is x, negative xi. Then when I do negative 2 times I is negative 2i. I'm going to put that in the I column. Negative 2 times 2 is 4, which I'm going to put over here underneath the 1. They're like terms. Negative 2 times x is negative 2x. I need a new column because there's no like terms. X times I, xi, is like terms with this one. X times negative 2 goes over here, and x times x needs a new column because it's x squared. So that gives me x squared minus 4x. These cancel, and 5. So x plus 1 times x minus 2 times x squared minus 4x plus 5. You can see now the coefficients are all going to be real. I just have to keep multiplying. So x minus 2, that's negative 10, positive 8x, negative 2x squared, 5x, negative 4x squared, and x cubed, which is x cubed minus 6x squared plus 13x minus 10, which I have to multiply by x plus 1. So that's negative 10, positive 13x, negative 6x squared, and x cubed, plus negative 10x, positive 13x squared, negative 6x cubed, and x to the 4th. So x to the 4th minus 5x cubed minus 7x squared plus 3x minus 10. And there I have written a polynomial function in standard form of least degree with real coefficients that has the given zeros. Oh, and I am out of time. So it's a good thing I'm done.